All right, so one last titration problem here. Make sure you can see this. Yes, you can. Okay, so one last titration problem. So you can see here, we have a weak base and a strong acid. Okay, so weak base, strong acid. Calculate the pH after adding 30 milliliters. Okay, so we look at our initial concentration. So we always have to look at the initial concentration of, this time it's our base because we're adding the acid to it. Look at our initial concentration. And then remember, so if we do that, just 25 times this, and we did this before. So this is like 2.5 times 10 to the negative 3 moles, just molarity times liters. So when we add 30 milliliters of a 0.1, that's 3 times 10 to the negative 3 moles of our acid. So now we have more acid than we do our weak base. So we are past our equivalence point, right? Always, always, always in titrations, figure out the moles of whatever you've got in your beaker, and then look at the moles of what you've added. And that's how you can tell if you're before, at, or after your equivalence point. So this time we know we're after our equivalence point. So after our equivalence point, that means we have mostly our strong acid, and our strong acid is strong. So pretty much it's so strong that the conjugate acid that's created when we dissociate our base is kind of like not important. Remember when we mixed like stronger weak acids with weaker weak acids, and we only considered the stronger one? Same thing here. So all we need to do is figure out how much strong acid we have. Okay, so we need to figure out how much HCl was used and how much we have left over. So you can see we had 3 times 10 to the negative 3 moles of this, and we have 2.5 times 10 to the negative 3 moles of this. Well, we're going to use all of this. So how much will we have left? We just subtract, and that's like, I don't know, what's it? 5 times 10 to the negative 4. I just subtracted the 2. So that's how many moles I have. But remember, we have to figure out our molarity, right? So if we do a moles table, so this is like my moles table, but I always do it in my equations. So we have 5 times 10 to the negative 4 moles of HCl over our volume. Remember, our volume is both the volumes. 25 plus 30 milliliters. And I always just take times 10 to the negative 3, makes my life easier. So that ends up being, I don't know, 0 point, calculator, 0.0091 molar. And then all we have to do is take the negative log of that. And that's our H plus. Okay, so let me get a moles table. I think I have, yeah, here's your moles table. Here's everything I just did all in one step. So this is how much we started with in our beaker. We added this much. Now, this we're gonna have extra, so we're gonna use all of this because we're gonna react it out. This is gonna go up, but again, we don't care about this because this is a weak acid. If we have a pH of a weak acid mixed with a strong acid, we just ignore the weak acid. So all we care about is our strong acid. Here's our moles, and then our volume again is 5 times 10 to the negative 4 over 25 plus 30 milliliters, and then times 10 to the negative 3 to get it to liters. And that gives us 0.0091 molar. So when you mix a strong acid with your weak acid, which is these two, you ignore the weak acid, and your pH ends up being 2.04. So that was the last of our titration problem that we had. Okay. So again, The video on titrations is in your, let me just go back here really quick. The video on all these titrations that I did is in here. Here it is, right? Put it in here. Well, I thought I had the video in here. Oh, there it is. So under the lecture, so that video, it's in the announcements, but it's also here under lecture. Make sure you can see this. Yes, you can. So here's all of the additional aqueous equilibria lectures. And then here is the one to watch before you do your quiz again, right? Also, I want to show you, these are from a student I had like 10 years ago. These are Evie's really, really beautiful titration notes. So here are exactly, so here's a strong base and strong acid. Here's like initial equivalence, and then here's strong base weak acid. So it's kind of like everything we're doing, and she just put it into this like cute little like baby tiny notes. It's the whole chat. This is the entire chapter in 1.5 pages of notes. So these are actually, people found these very handy. And I literally just call them Evie's titration notes because her name was Evie. Okay, so again, here is the video that you definitely want to watch, which will help you a ton for your exam and for your lecture checkup quiz. And then resubmit your lecture checkup quiz. And then I'll put the key up as soon as everyone submits it. And then here's the key to the quiz you had today. I put it up, and again, I really worked hard on kind of thinking through it for you, so you could see just not what the right answer is, but why it's the right answer. So like, here's like D, and here's why I chose D. Here's B and why I chose B, right? So I tried to, instead of just try to like bring you through the thoughts of these questions. Okay, so now we are going to leave titrations for even more fun. So we're still going to be doing ice tables because we're like never leaving our ice tables. Well, we will leave our ice tables, but not right now. So what if you have a polyprotic acid? And so if you have a polyprotic acid where your Ka is much bigger than your Ka1 is bigger than your Ka2, which is pretty much every single di and triprotic acid, you don't really have to worry about it because the Kas are pretty far away. And so they're pretty simple to do. By the way, I'm not going to make you do one of these. So there will be no polyprotic titration. You will not need to do any pHs of those with titrations. I'm just showing you that you can actually see 2 equivalence points with them, which is pretty cool. So really the only one you have to worry about is H2SO4, that you can see these differences. But again, there won't be any calculations with that. But just know if you do have a diprotic or a triprotic, you can see the different equivalence points here each time it loses a hydrogen. Okay, so when we're doing titrations, we used indicators in 219. So if you took chemistry, even if you didn't take it at SAC, you did titrations at some point in your life, I'm assuming. And when we reach the end point, that's that inflection point, right, where our acid equals our base. And to tell that, we used an indicator. Now let's look at what an indicator actually is, because believe it or not, it's just a buffer. So here's what we did. Literally, I think we did NaOH and HCl in 219 if you took 219 from SAC. Otherwise, you probably did this either in high school chemistry or another chemistry, but we used an indicator. But we could have actually used a program to do it also. So our indicator was one color here and then a different color here. So that's what we're going to look at right now. So a lot of dyes, which an indicator is just a dye, they are just buffers. So they're just weak acids and their conjugate bases. So the one we use is phenolphthalein. That's the one that we use that it turns pink at the end point. And so IND, that just means indicator. So it's just the weak acid and there's the conjugate base, right? And these are different colors. So this is one color and this is a different color. And so before the endpoint, it'll be one color, and then after the endpoint, it's at another color. When the colors are both mixed together, you get, well, when there's equal amounts of this and this, you get a blend of both of colors. And so when A minus and HA are one, like when the pH equals the pKa, that was on your quiz today, then the color is a mix of both the acid and the conjugate. When your A minus is 10 times greater than your HA, it's going to be a mix of mostly this, and then exactly the opposite, A minus HA, you're going to have mostly your acid color. Okay, so let's look at that in real life. So here's what we saw when we did titration last semester. So we added phenolphthalein and we saw nothing. Why did we see nothing? Because it was the acidic version, because in here was an acid. And then we added our phenolphthalein, which is our HA. This is what phenolphthalein looks like, by the way. It has no color. But then when we would add it, nothing happens, nothing happens, nothing happens, nothing happens. And we would see that pink, and then the pink would go away. And we see the pink that would go away. And then all of a sudden the pink stayed, right? At that time, we had both our HA and our A minus. So phenolphthalein as a base, conjugate base, is a super dark fuchsia color. Phenolphthalein as an acid is clear. When we have a blend of both of them, it's this light pink, right? So this is when the base is dominating. And so all an indicator really is a buffer. It's just a buffer that the conjugate acid, or the acid and the conjugate base, or base and conjugate acid, they're just different colors. So like, for example, methyl red, when it's in acidic solution, it's pink. When it's in basic solution, so here it's pink. Here it's a big one. Here it's pink, and here it's yellow. But when you mix them together, right, when your HA equals your A minus, pink and yellow make this interesting orange color, and that's how you can tell when you're at the end point. So that's what indicators do. And you can see this one is a blend here at 5, where this one is a blend here at around 8 or 9. So different indicators have different endpoints. So for most titrations, you can see that big change in the pH right near that equivalence point, and that's when you see the color change. And so that's what we did in Chem 219, is we used color, the change in color, to determine that, hey, yes, we are near our endpoint. And again, pH equals pKa at the equivalence point, because remember, pH equals pKa. This was on your quiz today, right? Log of base over acid. Or actually, I'm going to do A minus and HA just so we're doing this. So if this and this are the same, that ends up being 1. The log of 1 is 0. So when the pH equals the pKa is when we have the same amount of our conjugate acid or our acid and our conjugate base, or vice versa, conjugate base and our acid, base and conjugate acid. Okay. So now let's say you were doing a weak acid, strong base, weak acid, strong base, right? The endpoints are different. And so depending on where you think your endpoint is, you can choose different indicators. So again, you can see, like, if you were going to do, let's say here's our phenolphthalein, right? Here, right? That's about when the pH equals the pKa. Oh, and so that's like at a pH of 9-ish. So this one right here is kind of cool. So it's blue, and then it's HA is red. So you can see you get like a nice purple. So if you were going to do a titration where the end was between 5 and 6, you might choose this one, or you might choose methyl red because it makes that orange between 5 and 6. If you knew your endpoint was between 5 and 6, you wouldn't choose any of these because there's no color change at that point, right? You wouldn't choose this because it would only be yellow. So if you have a titration and you know about around where the endpoint should be, that's how you choose what indicator you're going to use. Okay, so those are our titrations with a little bit about our indicators. Now we're going to talk about solubility equilibria. And we sort of saw this a little, actually we've been seeing this in lab the whole semester. And we're about to change your rules about what insoluble means. So you know how in 219 and 209 or your intro chem and gen chem class, it said like, this is insoluble because I looked at a solubility table and it says it's a solid. Okay, so we're going to change this to there's no such thing as insoluble, right? There's less soluble and more soluble, but everything's a little bit soluble. And so we're going to change our definition of solubility table right now. So first we're going to look at the solubility product. Oh, look, KSP, which works the same as Ka and Kb and Kaq, right? They all work exactly the same. So let's say we've got an ionic compound and it's going to dissociate. Let me just use, well, let's use a real one. So this is just like a metal, non-metal. So it's going to dissociate into the metal and the non-metal. So if we look at our solubility table, I'm going to show you a real one because sometimes people don't like the pluses and the minus. Let's do PPCl2. So if you look at a solubility table, it says it's solid, which is insoluble. No, it's actually soluble. Just a little bit though. So if we were going to write the dissociation for PbCl2, which we've done dissociations, right? It comes apart into 1 Pb and 2 Cl minuses. And so remember, in an equilibrium expression, we don't put solids. And so if we were going to do our equilibrium expression, which we learned the very first day of class, right? It would be Pb and then Cl raised to the 2. Now we've been hanging in acids and bases and everything has only been coefficients of 1. So we got to go back to like the beginning of equilibrium when not everything was a 1 here with these exponents. So this would be the KSP for lead 2 chloride. Okay, and this is what we call a solubility product. Now here are some solubility products for some insoluble compounds. So remember, if the K is much less than 1, that means it's very, very, very reactant favored. So all of these are reactant favored, meaning when you put them in water, they don't want to dissociate, right? So when we put this in water, it wants to be over here because the Ks are so small. So all of these, if we looked at a solubility table, would say they are insoluble or only partially soluble. But look, they are a little bit soluble. So we're actually going to calculate from these KSPs how soluble these insoluble compounds are. So you can see some are more than others, and you can't really compare them unless the number of ions compare. And we'll actually look at that one. Like, for example, so this comes apart into the 3 ions and this one comes apart into 2 ions. So you can only compare like this is 3 ions and this is 3 ions. So you could compare those two. Just because when you write the KSP, the number of ions does matter. But we'll talk more about that in a minute. Okay. So again, what is solubility? The amount of solute that will dissolve in a given amount of solvent or solution. And so all these things we've said that are insoluble, well, I said they're actually soluble. The molar solubility is just the number of moles of solute that will dissolve in a liter of solution. So there's a difference between molar solubility and KSP. Right? So the molar solubility is the amount, so the number of moles that will dissolve. The KSP is like the Ka and the Kb and the, right? For some reason, people get the two of those mixed up, I guess, because they both have solubility in them. But I'm going to continue to try and draw a distinction between the two, just so you don't accidentally mess them up. Okay, so let's calculate the molar solubility of PbCl2 in water. Okay, so got to write the dissociation reaction because from the dissociation reaction, that's where we get the equilibrium expression. So here's our dissociation reaction. And I'm going to go on through these ice tables pretty fast because we should be very good at ice tables at this point. And so you can see you're not going to write, not going to care about this. Here's our expression for KSP. Now for these ice tables, I put S's to show their solubilities, but if you want to put X's on them, that's totally fine. It's all good. You can put an X there, right? So this one's going to, again, we've been in acids and bases, so we haven't had to do this much in the last couple weeks. We did before, so kind of dust those cobwebs off. There's 2 of them here, so there's 2 of them here, right? So don't forget about that part. So here we have, here's our KSP. And so our KSP, we just plug in S, 2S squared. Oops, oh, look, there it is. S, 2S squared. And then we just solve for our KSP. Where do we get our KSP? I think it was something times 10 to the negative 5th. I have it up here. It's on the table. Oh yeah, so the KSP is 1.17 times 10 to the negative 5th equals, combine this, so 4s cubed, divide by 4, and then take the cube root, and that will give us our S, which is 0.0143 molar. So this is the amount that will dissociate in our solution, which is not a lot. Okay, so I think I have, oh yeah, here it is right here, perfect. Yeah, right, so we just divide by 4, and then we just take the cube root. And here's our S. Okay, so, and again, we use our KSP just like we used our KA and our KB and our KAQ and our KP, right? All the Ks get used the same. So let's look at this reaction here. PBBr2. So PBBr2. So if we looked at the solubility table, it would say that this is insoluble, but it's not all the way insoluble. 2Br minus, right? Gotta write this dissociation because this dissociation is going to tell us what happens. This is a solid, so we don't put it in our equation, right? So our equation is going to be KSP equals PB2 plus times BR minus squared. This one's going to go up by S, up by 2S, again, because there's a 2 here. Oh, so S, sorry, my pen's going crazy. I don't need the pluses there. S, 2S, so KSP equals S times 2S squared. So that's 4S cubed. So it's pretty much the exact same problem we just did, just a different KSP. And the KSP here, there's your KSP. So here's what I just did. It's just nicer and prettier. So here's my KSP. I'm just going to change this. I'm doing this 2 different ways for you, so you can see there's different ones. So that's giving me my molar solubility. So if it's KSP equals, is it okay if I just go from here? 4S cubed, right? And this time they're giving us our molar solubility and asking us for our KSP. So our KSP, we can look, I think it was, I can't remember, I think it was -7, but we can look. But this time they're giving us our molar solubility. So we just plug this in here and solve for KSP. So I'm going to come right back because I don't remember what it is off the top of my head, and I don't want to say this wrong. And I can't go back beyond this. Okay, well, if you can see that table, I know it's tiny in your notes. But I can't see, it won't let me go back any further because my computer's doing its thing. Okay, so we plug in our solubility. And we just plug it in for 4S cubed, right? and we end up with KSP. I thought it was 10 to the negative 7. Let me see if I can find it in the book. Our KSP should be the same. So this is PBBR2. Making sure that this is correct. PBBR2 is 4.67 times 10 to the negative 6. Well, pretty close. Again, because of like math, sig figs, all these things, you might not get the exact same answer, but we should be able to get it. And again, this is the KSP. I'm just looking at it from the table. And so this one we just have to plug in. We didn't even have to do the 4s cubed part because I gave you the S. So I made it a little harder than it needed to be. So it's S and then S squared because they gave us this. So it's a little bit different than the one we did before. It's a little bit easier. Okay, so now let's use our KSP and the relative solubility. So molar solubility is related to KSP, but again, we can't compare KSPs unless they have similar ions in dissociation. And so they have to have the same stoichiometry. So if you had, I can't go back to my table, so I'm just looking at my table here. So for example, if we had PbCl2, this comes apart into 3 ions, and PbBr2, this comes apart into 3 ions. So we can compare these molar solubilities. So this one is 1.17 times 10 to the negative 5. And this one is 4.67 times 10 to the negative 6. So we can say that PbCl is more soluble than PbBr2. What we couldn't do is this. BaSO4 comes apart into 2 ions, and it is 1.07 times 10 to the negative 10th. So what we can't do is we can't say BaSO4 is less soluble than these two. We can't directly compare those. You would actually have to do an ice table because this only has 2 ions and this has 3. So if you're going to compare KSP, it has to come apart into the same number of ions. That's the only way you can compare the KSPs. This is different than Kas and Kbs, right? You can compare any Kb and any Ka, but for KSPs, it has to come apart into the same number of ions in order to directly compare them. Okay. Now let's look at the common ion effect with solubility. So if we add a soluble salt to an insoluble salt, it actually decreases the solubility. So Le Chatelier's is everywhere in this last piece here. So for example, if we add NaCl to PbCl2, it's going to decrease the solubility of PbCl2. Now why? When I add NaCl, it's got a common ion, Cl, right? Here is what we mean by the common ion. Cl is the common ion. When we add here, it's going to shift it this way, right? Remember our buckets? If you add more this side, it goes towards the reactants. If it goes toward the reactants, that's going to make more solid. If we make more solid, that decreases the solubility, which means we can get it to precipitate out of solution faster. So again, all Le Chatelier's, add more of this, shifts it that way, decreases the solubility. Okay, so let's look at some of these common ion effects. Calculate the molar solubility, that's S, of CaF2 in 0.1 molar NaF. So again, this Na is not our common ion, the F is the common ion. So we're adding extra F to this. So what should happen? I'm going to add extra this, which should decrease my solubility of calcium fluoride. So let's see if indeed it does. Okay, so let's look at the KSP. So our equation is just going to be S squared, right? So if we look at our ice table, and again, I'm going to kind of do these ice tables quite quickly because we've done so many of these. So we start with 0.1 of F. It's going to go up by 2S. But again, We're going to say S is small. By the way, let me think before I say this statement. S is small always works with solubility because the KSPs are so tiny. It always works, but you still have to like say it works. You have to explain to me why it works, which we'll look at in just a second. We got to have our KSP here first, which I can't look back to my table, so I can't tell you what it is yet. So again, we just plug this in. We assume this is small. So it's just S times 0.1 squared. Our KSP, I have it on the next slide. Our KSP is 1.46 times 10 to the negative 10th, right? And so because the difference here, like 0.1, 10 to the negative 10, the difference is 9, 10 to the 9th. You're in no danger of the S is small failing. So S is small always works. So we plug this in. Here's our KSP. Plug this in here. Solving for our solubility. And so our solubility is 1.4 times 10 to the negative 8th molar. That's the solubility of our CaF2 in extra NaF. Okay, so now we're going to try another one. So really the key to these is writing that first equation, right? Writing that first equation, figure out what you're adding, like where are we adding this into our equation. So let's try this one. So determine the concentration of silver ions in seawater that has a chloride concentration of 0.55. And then here's your KSP of AgCl. So we want to know what is Ag if Cl is this. So we have Cl, all we need to do is solve for our Ag. This is a pretty simple solubility because there's no coefficients. So it's just straightforward. We have an initial concentration of 0.55 molar. So that's our initial concentration. Again, this is just going to be S. This is going to be 0.55 plus S. But again, I'm going to assume this is very small. Should be fine. Because my KSP was 10 to the negative 10th. So because the difference is 10 to the 9th, I am in no danger of my S is small not working, just like we did our X is small after we make this assumption. So I'm going to plug this in, assume this works. And again, so on your exam, when you take your exam, you would be like difference is 10 to the 9th, S is small, or X is small is valid. Or you might just go difference equals X is small, right? You have to know some kind of like a, hey, I know my S or my X is small because the difference is greater than 10 to the 3. Somehow you have to show that you know how to do that. Okay, so we just plug in our KSP, which was 10 to the negative 10th, and we're solving for our Ag. So we're trying to figure out what is the concentration of Ag if Cl is this, right? So this is Cl. So solving it ends up pretty fast. So S is 3.2 times 10 to the negative 10th molars. So that means when chlorine is 0.55 molar in seawater, silver is 3.2 times 10 to the negative 10th. So that is the amount of silver that is in seawater if chlorine is this. Okay. So that's solubility. So now we're going to look at solubility and how pH affects it and how we can precipitate certain ions based on specific conditions. So the effect on pH and solubility, we've actually done this one. We did this with aluminum, and we'll talk about aluminum a bit today, but we'll talk about more when we go to complex ions. So for insoluble ionic hydroxides, the higher the pH, the lower the solubility for most of them. And the lower the pH, the higher solubility. Okay, so what does that mean? So if we have a higher pH, we have more OH, right? Which again, Le Chatelier's principle says will drive it towards the reactants. So it will decrease the solubility. So if we have a higher pH, it's going to decrease the solubility. So in general, for insoluble ionic hydroxide, the higher the pH, the more the OH, the lower the solubility because of Le Chatelier's principle. And because of Le Chatelier's principle, the lower the pH, the higher the solubility. So the lower the pH is, the higher the solubility. So I can use this here, or I'll do it with another one too. If we decrease the pH, that means that the H3O plus is going to react with this, which is going to decrease the concentration of our OH, which will then again, remember our buckets? If this one goes down, it's going to shift it this way. So if you have an insoluble ionic compound, if you lower the pH, you increase the solubility. So let's do carbonate, right? So here is our insoluble carbonate. And so when we add an acid, the acid is going to react with this base. And when that happens, this is going to decrease, which will make it shift this way, which again, that means it'll increase the solubility, meaning more of this will become ions. So here's our acid reacting with our conjugate to make more of these. Oops. And so this will decrease here because it reacts with the H3O plus. So that's how pH works on solubility. This is why in your lab it says like, make sure it's basic, because if you have an insoluble ionic hydroxide and it's not basic enough, right? If it's not basic enough, you won't see the precipitate. And so that's why a lot of times it's like, oh, make sure it's acidic, make sure it's basic. If you got an insoluble ionic compound and we want to make sure that we dissolve it all, right? We have to have our pH has to be low enough to drive it over to the right. And that's why a lot of times I'll be like, maybe add a couple more drops of this, because what I'm trying to get you to do is move your pH or move your solubility one way or another, right? Okay, so now let's look at precipitation. And we're actually experiencing this lab in this in lab. Literally every time we're in lab, we're doing this exact same thing. So precipitation, making solids, precipitates, occurs when the concentration of the ions exceed the solubility of the ionic compound. So we need to compare our Q's and our K's. So remember, Q, good review for your exam. Q is just like K, it's just not at equilibrium, right? So K is at equilibrium. Q is just not at equilibrium yet. So we use Q to figure out which way are we going, right? And so if Q is the same as K, that means we are at equilibrium. If Q is less than K, that means it's going to go forward towards our products. Remember that? If Q is greater than K, we're going backwards towards our reactants. Now let's just think of, I'm just going to do PBCl because we've been using that one. Right, and these are AQs, AQ, solid. So if you think of your Qs and Ks here, if our Q is less, so if our Q is equal to our K, right, then it's saturated, meaning we've got no solid because we're at equilibrium, right? Or no selective precipitation. We'll look at this one. If Q is less than K, then it's going to go this way towards solubility. If Q is greater than K, that means we've kind of overshot it and we're going to go back this way and we're going to make a solid. So, and sometimes we can get a supersaturated solution. And remember, a supersaturated solution just means it's holding more than it should be able to at a specific temperature. Okay, so let's see. Will a precipitate form when we mix lead 2 nitrate with sodium bromide if the concentrations before mixing are 0.05 molar and 0.035 molar? Okay, so we're going to react to this with this double displacement reaction, right? All the way back. Remember double displacement reactions? Yeah, double displacement reactions. Just going to write it for you because I'm assuming you know how to do your double displacement reaction. So here is our solid. That's what we're making. So the question is, will a precipitate form? So what do we have here? So again, we only think in net ionics in this world, right? So that's a spectator, that's a spectator. So we need to figure out how much do we have of all of this. So we have 0.015 of this one. And we have 0.035 of this one. Right, and I'm literally just doing straight net ionic right from there. So this is just our Pb2 plus, and this is our Pr minus. It just changes into a net ion equation. Okay, so again, here we have this much of our Pb, this much of our Br minus. Okay, so this is what we care about. So we need to know the KSP for potassium, for lead 2 bromide. Here's our KSP. Our dissociation reaction is this. So we had a double displacement reaction, turned it into net ionic, and this is what we care about, right? So now if we write our Q, so our Q is the same as our K, so it's just going to be Pb times Br squared. That's going to be our Q. And then we just plug in our numbers. Plug in our Pb, plug in our Br, and that's not the right answer. I can't edit it anymore, it won't let me. This is the right answer, 1.84 times 10 to the negative 5. So the question is, will it precipitate? To tell if it will precipitate, you have to look at the KSP. So the KSP is 4.67. So 1.84 is bigger than 1.84 times 10 to the negative 5th is bigger than 4.67 times 10 to the negative 6. So Q is greater than K. If Q is greater than K, that means we're too far towards our products and we're going to swing back to the reactants. So yes, PPT will form. So remember, if Q is greater than K, swinging back toward the reactants. So that means that here we had too much of this, and so it's going back that way. So it will precipitate. Precipitate will form. So this Q and K is great review from what we did. Seems like forever ago when we did Q and Ks. Okay, let's try another one. Try to color code these for you so you can kind of follow them a little bit easier. Okay, so now, will a precipitate form when we mix this with this? So what are we going to do? First, double displacement reaction. Figure out what's solid. Here's our solid. Then we turn it into a net ionic equation. Spectators, spectator, spectator. Don't care about our spectators, right? So we care about Ca and OH minus. Right, so I just turned it into a net ionic equation. I feel like we're getting good at net ionic equations now that we've done so many of them in lab. So what do we have? Oh, we have the same amount of both. Nice. Both are the exact same amount this time. So what are we looking at? We're looking for the KSP of this. So we look at the table, which unfortunately I can't, my computer won't let me go back to the table. But here's the KSP from that table. So when we write our reaction, we're just going to have Q equals S times S squared because it's 2 or X's. And so then we just plug them in. So it ends up just being 0.0175 cubed. That equals our Q. And so Q equals 5.36 times 10 to the negative 6. So we just cube it. So what do we do with this again? Compare this to this. If Q is greater than K, yes, precipitation. Q is less than K, no precipitation. Here's that exact same thing, just nicer. So our Q is indeed barely bigger. So it does indeed precipitate, but barely. Okay, any questions on these with our Q's and K's so far? Because we're gonna go crazy with them in just a second here. Any question with these Q's and K's? We're okay with these? Okay. So I'm going to try and go slow on these now. Question on this one is, what is the minimum concentration of hydroxide necessary to begin to precipitate magnesium if the concentration of magnesium is 0.059 molar in seawater? And I gave you the KSB. I remembered it this time. Okay, so what is the minimum concentration of OH if magnesium is 0.059? So we must be dealing with magnesium hydroxide here, right? Our KSP must be of magnesium hydroxide. Why? Because all we're given is magnesium and hydroxide, so it must be magnesium hydroxide. So my dissociation is going to be this. So I can see my equation, I got a 2S here and an S, right? I'm not even really drawing my ice tables now because I'm assuming that we all know how to do it straight without them. So when something begins to precipitate, it's just after, right? Just when Q is a little bit bigger than K. So it begins to precipitate when Q is K. That's like right at the beginning, like right when it starts. So then Q, again, this is squared because there's two of them, right? And so it's telling us that this is 0.059 molar. And then this is just OH squared. And our Q equals, I gotta figure out our Q. Our Q, here's our part. What is Q? If it just begins to precipitate, you could use a greater than sign here, but we're just gonna say equal and say anything more than. So it just begins there. So that means that when our Q is K, then it will begin to precipitate. So question is, when magnesium is this, what is the concentration of OH when it begins to precipitate? And so we just plug this in. And again, this part, I'm assuming that we all can we're just solving for X here, right? Divide by, take the square root, right? Divide by 0.059, divide by 0.059, and just take the square root. And that's going to give us our hydroxide concentration, right? I just have it all here for you, so we know how to do that. Okay, so what does this mean? This means that the concentration of OH is 1.9 times 10 to the negative 6 when it just begins to precipitate. So when magnesium, the concentration of magnesium is 0.059, concentration of hydroxide is 1.9 times 10 to the negative 6. So again, these are tiny numbers because these are insoluble, which means very, 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 very little of them are actually ions, right? It's almost all solids. Okay, let's try another one. So in this case, remember, the precipitation happens when the value of Q just equals K. So that's why we set Q equal to K if we're looking for one of these minimum concentration questions, right? So the concentration above is when it will precipitate. So we say it starts to precipitate when Q equals K. Okay, so let's try one more. So again, what is the minimum concentration? That's one of those Q equals K. So when something will precipitate is when Q is K. Well, directly above that. So we just say when Q is K. So we've got, what is the minimum concentration of calcium nitrate that will precipitate calcium hydroxide from 0.1 molar, 0.0175 molar sodium hydroxide? Oh, okay. So let's figure out what we have here. So this is our solid. Why? Precipitate. It means this is a solid. So we're adding this plus this. So this is our double displacement reaction, and this is our product. So this is what they're talking about. So we want to know the concentration of this, which again, changing it straight into an anionic here. Spectator, oops, need that too. Spectators. We really only care about, again, we only care about the net ionic equation, right? So just our net ionic equation, that's all we care about. And when something begins to precipitate, that's when our Q equals K. So it's going to be Ca times OH squared. Okay, so remember Q equals K. So K is our Q. And we want to know what is the minimum concentration of CaNO3. Well, this is our CaNO3, right? Because when CaNO3 dissociates, it's one Ca and two NO3s. So therefore, Ca is CaNO3. They're going to have the same concentration. Ca is going to have the same concentration as calcium nitrate. And our concentration of this one is 0.0175, right? Because calcium or sodium hydroxide is our OH. That's where our OH is coming from. It's coming from our NaOH. It's coming from right there. So we just plug this right there. And then we solve for this. So Q equals KSP, that's when it precipitates. Plug in this for our OH, plug in this for our Q, solve for calcium. So that means when we have 0.0175 molar sodium hydroxide, which again, don't care about the sodium. So when we have 0.0175 molar hydroxide, our calcium concentration is 1.53. And again, because of our dissociation reaction, this is also calcium nitrate, right? Both of these are the same. Okay, so we're going to try one more of these. This one's actually really fun. Right. So what is the magnesium concentration when 0.011 molar calcium just begins to precipitate from seawater? Okay. So what's the magnesium concentration when 0.011 moles of calcium begins to precipitate? So this means that calcium is going to precipitate. So calcium is going to precipitate as, and again, well, I kind of give you a hint here. I tell you the KSP. So that means calcium's precipitating from CaOH, right? And so again, when it begins to precipitate, that's when Q equals K. Okay, so we write our Q here, our equilibrium expression, which is super similar to all of these. So let's think through this one for a second. So what we're trying to do is we're trying to figure out what magnesium is. So again, magnesium is going to be coming from magnesium hydroxide. Calcium is coming from calcium hydroxide. Okay, so we have the concentration of calcium. It's given to us. So what we need to do, so when calcium hydroxide just begins to precipitate, that's when the Q equals K for CaOH. That's when it precipitates. So if we can figure out the concentration of this OH, then we can use this concentration of OH. We can plug it in here and use this KSP to figure out the concentration of magnesium. So it's kind of like a one goes to another, goes to another. Okay, let me explain that one more time. Okay. Kind of fun, but they're kind of like brain twisters all at the same time. So calcium comes from calcium hydroxide. Magnesium comes from magnesium hydroxide. They're telling us how much calcium we have. And it begins to precipitate. When it begins to precipitate, that means the Q equals K. So if they're giving us calcium, we can solve for our OH. Whatever the OH is here is also the OH here because they're both in seawater, right? So from there, we can use that hydroxide to solve for magnesium. So first, we're going to find this. Let's find this hydroxide. Right, here's our KSP, gave that to you. And again, we plugged, here's our calcium. Oops. I'm just gonna get rid of all this so you can see this. Here's our calcium, which went here. And I just plugged that in here. Our KSP, which was here, we just plugged in here. We're solving for our OH, right? So just divide by 0.01, take the square root. So this is the concentration of OH when calcium hydroxide just begins to precipitate. So when we first get our first solid calcium hydroxide, the OH concentration is 2.06 times 10 to the negative 2. So now we're going to use this. We're going to plug it in there and solve for magnesium. So we're going to then use the magnesium hydroxide KSP to solve for magnesium. Okay, that's our plan. So we don't really need this. I was just showing you it before. Okay, so this is it. This was our calcium hydroxide. This again, same problem. I'm just taking our number here, right? Taking our OH. That's our OH, right? So now, again, magnesium comes from magnesium hydroxide, and we're going to plug this in here, solve for magnesium. So here's our KSP for magnesium. So again, we're going to use Q equals K when something begins to precipitate. So we're just going to use this in our Q. So this goes here. This goes here, oops, this goes here. This goes here, and we solve for magnesium, right? So it's kind of keeping all your ducks in order, but it's actually kind of fun. It's like a little brain teaser puzzle. So when we do that, I just plug this all in, solve for them both, right? They're a little similar because they're both 2.06, but check out the exponents. They are not the same. And we get this. Okay, so what does this even mean? So this means when our calcium begins to precipitate out, the magnesium's concentration is 4.8 times 10 to the negative 10th. Okay, that's what it means. So magnesium's concentration originally in seawater was 0.059. So when calcium just precipitates out, the magnesium dropped from 0.059 to 4.8 times 10 to the negative 10th. All right, questions on this one? This one's kind of like, kind of crazy. So basically, we used our calcium. From our calcium, we got our hydroxide. From our hydroxide, we used that one to get to magnesium. So you just got to remember, kind of keep your ducks in a row of which one we're doing when. All right, next question. Very similar. Oh, we're back to there. This is, by the way, this is where I was getting all those KSPs from this table. Okay, a solution is made by mixing lead nitrate with silver nitrate. So both compounds have a concentration of 0.001 molar. Sodium chloride is added to precipitate out both AgCl and PbCl2. What is the silver ion concentration when Pb2 plus just begins to precipitate? Whew. Okay, so we're going to mix lead nitrate with silver nitrate, right? And then we're going to add silver chloride to that to separate out silver chloride and lead 2 chloride. We want to know what is Ag when the Pb just begins to precipitate. Okay, so got to figure out what Ks we need. So here's lead chloride. So we're going to use this KSP. And I got silver chloride. So these are our 2 KSPs we're going to use, right? So we're going to be using both those KSPs in this question. So the question is, what is silver when lead just begins to precipitate? And so we have to remember, like, when we're doing this here, plus Cl, right? 2 Cl's minus plus 2. So this concentration we need to get. So when we do that, what's the concentration of this? And we're going to figure out this one too, right? Okay. Both compounds have this concentration, right? So lead nitrate is going to be 0.001, and silver nitrate is 0.001. So basically lead and silver are both 0.001, right? It's basically what they're saying to us. Lead and silver are both 0.001 molar. Okay, so now we're gonna start. I need more room. So here's basically what we did, right? Double displacement reaction. We're gonna start with this one first. So when it just begins to precipitate, Q equals K. And again, we decided that both of them are 0.00. Well, we need to figure out what silver is. We don't know silver, but we know lead. So Q equals K, red or Q, very similar to what we've done. I don't have Q on here. Q is 1.17 times 10 to the 5th, which is K. Well, K is 1.17 times 10 to the negative 5th. And lead is 0.001 molar. And we're going to figure out our Cl. Okay. And then we're going to use that in our next piece. So again, we're just going to solve for x, right? Divide by, take the square root. Oh, here it is, right? Divide by, take the square root. And this is our chloride ion concentration. Okay. So now here's our Cl minus concentration. We're going to use that 1.08 times 10 to the negative 1. I don't need this. Here it is. This is the one we need. 1.08 times 10 to the negative 1. Okay. So now let's figure out our AgCl. So we already know our Cl. Now we're going to calculate our AgCl. This is going to come from our KSP. Our KSP, which is our Q, which is 1.77 times 10 to the negative 10th, if I remember. So we're going to have 1.77 times 10 to the negative 10th equals whatever Ag is, this is what we're trying to figure out, times Cl, 0.08 times 10 to the negative 1. So we just divide these two. I did this right, and we get this. So what does this mean? So when PbCl, so Pb2 plus, begin to precipitate out as lead 2 chloride, the silver ion concentration is now 1.6 times 10 to the negative 9th, right? Originally, if we did the question, like we did the question before, it was 0.001. So it was 0.001 and it dropped to this, right? That's that common ion effect, right? So our solubility dropped from at the beginning to 1.6 times 10 to the negative 9th molars, which we'd expect it, right? Common ion effect says when you add a common ion, the solubility should decrease. Indeed, our solubility did decrease. So these problems aren't too bad. Just kind of have to kind of remember you got to grab whatever that common ion, solve for it, use that common ion in the second equation. So in this case, that common ion was chloride. So find your common ion, use it in the second equation. Any questions on these? Okay, we're going to talk for just like a minute about complex ion formation. We talk about complex ions like in great detail later in the semester, so we're only going to talk about a little bit. But we have, right? You have a bunch of complex ions, 3 of them that a lot of you guys made today in group 3 in the lab, right? So complex ions, they bond with what we call a ligand, which is kind of like the extra little piece. So like water is a really good ligand. It means it's attached to it. And so you can see there's like 2 waters attached to silver. So the ligand here would be called water. In this case, water is a Lewis base. It donates the electrons. It donates those lone pairs of electrons. And so ions form by combining a cation, sometimes a cation, sometimes an anion, with several anions or neutral molecules. And these are complex ions. And whatever's attached to it is called a ligand. So in this case, again, water is our ligand. There's 2 ligands, there's 2 waters attached to our silver, and that's our complex ion. And so here's what we're forming in our complex ion. So when we do complex ion equilibria, very similar to everything we did. So ammonia is a very, very popular complex ion, which we're going to, a very, very popular ligand, which we'll talk about a lot later, but only a tiny bit right now. So if you have silver with water, and then you add ammonia, silver would much rather be with ammonia, much rather be with ammonia. So it would form this complex ion. Usually we just write this without water. So if I write this without water, it just turns into this, right? And so if I was going to write an equilibrium expression here, I would have my products over my reactants, and this one would be raised to the 2. So this we just call KF, the formation constant. But again, it's another K, but they all work exactly the same. This is just talking about specifically complex ions forming, right? And don't worry about these questions. I'll teach you how to figure out these equations. So you see how, for example, this is the complex ion, so there's 2 NH3s. So when you start, oops, there's 2 NH3s. That's literally how you just need to look at the KFs and you can figure out the equations. They're really not that hard. So like you can see this one, this copper here is a copper, and there's 4 NH3s, and that makes Cu NH3 4. They pretty much all work exactly like that. So the equations, as long as you have the complex ion, you can write the equation, right? But you can see some of them kind of crazy, like this one. It's 6 ammonias. So this is Ni plus 6 NH3s. Makes Ni NH3 6. I'm not putting the charges on there because it's easy, but look at the KFs. Like this is going to be raised to 4. This one's going to be raised to 6. Yeah, they're kind of crazy. Okay, so let's just do one of these quickly. So we have 200 milliliters of 1.5 times 10 to the negative 3 molar copper nitrate solution mixed with 250 milliliters of a 0.2 molar NH3. Okay, what is the copper at equilibrium? So NH3 is a big fan. So we're going to look at, I'm going to go back and I'm going to say, okay, which one is copper and NH3? Here it is. It's this one that I wrote right here. Copper and NH3. So it's this equation. That's the complex ion equilibrium equation we're going to look at. And there it is right there. So when you write it, products over reactants raised to the coefficients. Yes, we have to raise this to the 4. So we need to figure out, so we want this. So we need to figure out this and this. And it's telling us we need to figure out how much copper we start with. We want this at equilibrium. So we need to figure out how much copper are we starting with? Well, 200 milliliters of a 1.5 times 10 to the negative 3. That's how much copper we're starting with, right? Because when this breaks down, it's Cu plus 2 NO3s. So this is the amount of copper we're starting with. Seem kind of ice table-ish, isn't it? Yeah, it is very ice table-ish. And then our NH3, we can just get from right here. And we're mixing them together. So all we need to do is remember, since we're mixing them together, that our total volume is those two added, right? So our copper is just our, we have to get to our moles. I'm going to do this one fast. I'm going to do this one slower, and then I'm going to do ammonia quicker. So we get molarity times liter. So 0.2 times 1.5 times liters times 1.5 times 10 to the negative 3 equals our moles of copper. And then our volume is now going to be 0.2 liters plus 0.25 liters. Right? And that's going to be our new molarity. So we have to find out the molarity of copper at the beginning, and then our molarity of NH3 at the beginning. So here we are. Here's the molarity of copper. Do the same thing with the molarity of NH3. So these are our initial concentrations, but we need the equilibrium concentrations. So it's an ice table. The difference here is this X isn't the change this time. So it's not the change this time. So this one's a tiny bit different with what people believe. This is the, I wish we should not use X. We should use like, I don't know, something else besides X. So this is actually the amount at equilibrium, right? So in this case, when we do this part, copper is going to go down by this because this formation constant is so big, 10 to the 13th. All of the copper is going to change, right? This copper, all of this is going to disappear because this is so big, this Kf lies so far towards the products, it's all going to go away. And this NH4 is much bigger. So this one's going to go down by 4 times. Because it's 4 times whatever this is going to be. Not all of it's going to go down. But by the way, that ends up not even changing our number. And this is going to go up by 1 of those. Okay, so that's our ice table. Kind of, I mean, it's an ice table, but it's not a change this time. It's more of a moles table with molarity. And then all we do is solve for X. So we're just going to solve for this and plug the rest of them in. And when we do that, we get 2.7 times 10 to the negative 13. And so that's the amount of copper we have in the end. And again, we don't really need to look at the X as small. It always works because this is negative 13 and this is negative 4. This is a way you could do this where you don't actually have to find it now. And again, on your exam, I'm okay if you do this. You say, oh, negative 4 is so much bigger than negative 13. The approximation works. Okay. Okay, so we're gonna have to stop there. So this is our new concentration. This is the concentration of copper at equilibrium. Again, it's similar to what our ice tables were before, but this time we're actually just solving for our X, and our copper is reacting with this. This can only go down by our smallest amount. It's all going to go towards products. In the end, we're only going to have this, or mostly this left. As you can see, the amount of copper we have left at the end is barely any copper left at the end. 2.7 times 10 to the negative 13th. That's the amount of copper we have in the end. The reason we have such a tiny, tiny number is because this KF is so big, meaning it's super, super, super product favored. So this uses the combination of knowing K, the product favored, and a little bit of your ice tables with a little bit of your moles tables with a little bit of complex ion knowledge. Okay, so I went over by a minute. I know some people have class. We'll finish the rest of this on Wednesday. But again, make sure you watch that titration lecture and resubmit your lecture checkup quiz, because that's kind of your only evaluative thing that I get to do to help you before your exam. So make sure you resubmit that, and then I'll grade those on Wednesday. So submit those by tomorrow evening so I can have them graded for lecture. Okay, so that's all we have today. I know it was a lot. I hope everyone has a good day, and I'll see everyone on Wednesday for lab. All right, goodbye, everyone. Have a good day.